Okay, welcome to Chapter 15, Waves, where we will begin our discussion of waves and waveforms and wave equations. We'll start with the big two kinds of waves. There are mechanical waves and there are electromagnetic waves and matter waves. Electromagnetic waves and matter waves are all of next semester, and so we're not going to recover those, at least not today. We're going to specifically talk about mechanical waves, and so these are things that need matter to travel through. Okay? So these mechanical waves are things that require matter to travel through them. That is solids, liquids, and gases. And so like you've probably heard before that you can't hear sound in space. Well, that's because there's no matter. There's no air in space for which sound to travel through. And so sound is a good one. Ocean waves is another really good example of these mechanical waves. And then even when we talk about these mechanical waves, there's two other kinds that we'll talk about. There are longitudinal waves and transverse waves. So we can think about longitudinal waves in using the idea of a slinky. So if I take a slinky and I stretch it out, and then I just push on one end, well, these coils kind of travel down to this end, and then they'll reflect off my other hand and go back. Longitudinal waves have a couple of parts to them. They have these areas where the springs or the coils are close together, and those are called compressions. And then there's these spaces in between that are really, really spread apart, and those are called rarefactions. And so compressional waves act by compressing matter longitudinally, back and forth horizontally. Two really good examples of this are sound waves and earthquake P waves. The primary waves out of an earthquake move the surface of the earth back and forth, not up and down. Then there's this other kind of wave, and this is the traditional kind of wave you think about, and that's a transverse wave. A transverse wave is something that goes up and down. Transverse waves at the tippy top are called crests. At the bottom, they are called troughs, like a horse trough. And these have some words that we recognize, right? Amplitude, wavelength. Amplitude is the distance from the middle, right? From that neutral ground, just like our oscillations, to the very top, or the distance to the very bottom. It is never the entire distance of that wave. It's only from the halfway, from the midpoint. And then transverse waves also travel up and down and horizontally. And so this would be like water waves or earthquake S waves. The secondary waves that earthquakes send out actually do move the ground up and down. Right? And so when we look at these earthquake waves, earthquakes send out two kinds of waves. They send out their primary waves, or P waves, and then their secondary waves, S waves. The primary wave kind of just compresses and expands the material within the earth and sends it on up. The secondary wave moves in both up and down direction, and it travels through the earth. Right? For either of these waves, one of the most important things that I want you to know is that while a particle might move as a result of the wave, the net movement of something doesn't change, right? And so these little black squares, for instance, as the P waves and the S waves travel through them, they move with the wave, but then they return to their original position. We see this a lot in the ocean, too. If you see something kind of floating on top of the waves, it'll go up and down with the wave, but when the wave passes, the thing is back where it started. It's in its original position, right? The same is true of matter waves. As I speak or as you hear sound, the air molecules are moving, but after they go through the compressions and rarefactions and the sound wave is over, well, then that air molecule returns right back to where it started before the wave traveled through. All right, so we're going to move on to specifically talk about sound waves, which are these mechanical longitudinal waves. Mechanical means they need matter, and then longitudinal means they have those compressions and rarefactions, right? Particles always return to their original position. Sound is an interesting thing because it depends on the medium which it is traveling through. Sound travels fastest through solids, and then faster in liquids than in gases. And so that's kind of funny because this is actually where you hear most of the sounds, and that's where your ears are adapted to hearing it. But sound travels much, much faster in solids and liquids, right? And this has to do with the spacing of the atoms. There's more matter kind of compressed into those states. And so because sound waves require matter, right, they require those atoms to bump up against each other and create compressions and then kind of space out and make rarefactions. Because there's more matter in the solids and the liquids, that sound wave goes faster through them. This other kind of idea is one that you know, but I'm going to put some words to it, and that is that soft materials absorb sound, right? They just kind of soak it right up and distort it, and then hard materials reflect sound, right? And so this is kind of the difference between, screaming into a pillow and yelling in a canyon. When you yell in a canyon, those are hard surfaces. Your sound wave travels to the rock layers or the cliffs, and then it bounces right back off, and we call that an echo. E-C-H-O. An echo is a reflection of sound. Right, and soft materials just don't do that. And so things like insulation or ceiling tiles or the big cushy things around your Beats headphones, right? Those absorb sound so that you don't disturb others and others don't disturb you. Hard materials, again, reflect sound, so like tile or rock, concrete. If you've ever moved into an empty house, you know that before you put all your soft furniture in there, they've always got an echo. All right. I'm going to talk real fast about the properties of a wave. So I've got a transverse wave here. Oh, no, I'm sorry. I've got a longitudinal wave here and a transverse wave here. This one has a crest, a trough, and an amplitude. For the transverse waves, it's really easy to see that the wavelength is the distance for one whole wave. So it's from crest to crest, or from trough to trough. If you wanted to be real creative, you could do a wavelength as like that. It doesn't matter where you measure it from, it's always the same. So no matter if I take this measurement or this measurement, I'll get the same wavelength. But the wavelength is just the length of one wave. For a longitudinal wave, the wavelength is equal to the distance between compressional sections. Or if you wanted to do the distance between rarefactions, you could do that. But you kind of go from the center of the compression to the center of the compression, and that's your wavelength in that form. Right? So if all sound waves travel at the same speed in air, what determines the frequency of that sound wave? And so remember, frequency is how much wave passes a given point in a second. Right, and so in sound waves, frequency is actually associated with the pitch. When you have very high frequency waves, high frequency, by the way, means short wavelength, so I get lots of waves in a second. Low frequency means longer wavelength, and so I get fewer waves in a second. High frequency noises or high frequency sound waves have a high pitch, right, like a woman's voice. And then very low frequency sound waves have a low pitch, like a baritone in a choir. Amplitude, right, this idea of the tallness of a wave, in sound waves, there we go, amplitude in sound waves is related to the loudness or the intensity. And so as I raise my voice and create a louder noise, I'm actually moving more air particles kind of in this vertical direction. And because I'm moving more air particles, you experience that as a louder noise. And so as amplitude increases for sound waves, the loudness and scientifically what we're going to call the intensity of that wave also increases. And so I definitely want you to know that frequency, right, is associated with pitch, and that amplitude is associated with the loudness of a sound. Right? To give you an idea of the frequency, or kind of what frequency is, humans hear, right in this 20 kilohertz range. And so remember, 20 kilohertz is really 20,000 hertz. There we go. And humans hear right kind of in that 20,000 range. There are other sounds, though, even if we can't hear them. If you ever have had a dog as a pet, you probably know this, right? They hear things that you don't. So just because we can't hear them doesn't mean that they're not there. The other sound that you're very aware of is ultrasound, right? Ultrasound are extremely short wavelength waves. They're very, very high frequency, so we can't perceive them with our ears. But they're these little sound waves that get sent out from a medical device, and as these sound waves get sent into your body to look at maybe like a bad knee or a growing baby, whatever surfaces in your body they're trying to examine, those sound waves actually reflect back, and they're all digital, and so they come back to the sensor, and we're able to actually get a picture of what's inside of you based on the way it reflects sound waves, right? Remember that whole hard materials reflect, soft materials absorb thing? That's how ultrasounds work, right? For sound waves, they also, I kind of alluded to them traveling differently in different states of matter, fastest through solids, slowest through gases. And sound waves actually travel at different speeds, depending on the medium that they travel through. The velocity of a sound wave is the change in distance over the change in time. And we can think about this as the wavelength divided by the period, right? And so we use the symbol lambda for wavelength. How long is this thing from compressional section to compressional section? And how long does it take for one whole cycle of a wave to pass by any given point in time? And so this will be in meters per second. We can also express this as wavelength times the frequency, because remember, frequency is just 1 over the period. And so this is the traditional formula for speed of any wave. The velocity of a wave is equal to its frequency in hertz, right? Times its wavelength in meters. Page 42 in table 15.1 actually gives you the speed of sound in different mediums. And so that's something that you can use when we talk about whales in the ocean, or a plane flying through cold air, or a plane flying through warm air, right? Sound depends on the place and the type of medium that it's going through, and this will be a very, very, very handy resource for you to get the speed of sound, right? And then from there you can find things like the wavelength or the frequency or the period, once you know what medium you're talking about, right? All right. This has always been really neat to me as just a scientist, that all different animals can hear different ranges of sounds. They can hear different frequencies. And so let's see. Humans are right here, right? And this is sound wavelength in centimeters that we can hear. And this is frequency in kilohertz down here at the bottom. So I'm going to talk about it in terms of frequency, kilohertz. So humans can hear from about 20 hertz to about 20 kilohertz. We have a pretty big range, right? But then things like bats and rodents and moths and crickets can hear much, much higher frequencies than us. Conversely, whales and fish, right, can hear much lower frequencies than us. And like I said, if you've ever had a dog, you've definitely experienced this, where your dog or your cat hears something it's beyond your range of hearing, right? Or it's below your range of hearing. Humans' range of hearing is just well equipped to the environment that we've adapted to, which is living on land. And in order to do that, we need to hear sounds in gases, right? Whereas like whales and fish need to hear sounds in the water. And then bats and rodents and moths and crickets all have different frequencies that they communicate at. All right, so we're back to this idea of intensity. And remember, intensity is associated with the amplitude of a sound wave. And we, as common people, know this as like the loudness of a wave. Now, the intensity of all waves can be measured as a power over area, And yeah, this is power in watts, just like when we talked about energy and work and power. So this is power in watts, or this is also watts as in joules per second, right? Over the area, which will be in square meters. But for sound, this is a really funny unit because we don't think about sound as like actually doing work, right? And so what we do is we take the intensity in watts per meter squared, and we actually need to convert it to a sound unit called decibels, right? So to convert intensity to decibels, the first thing we need to know is, well, if we're right at a sound source, then its intensity is just its power divided by, then its intensity is just its power, right? Watts per meter squared. But if I'm far away from a sound source, it actually is, the amplitude kind of decreases. So as that wave travels through lots and lots of matter, it encounters kind of friction in the atoms, and it dissipates in its energy, right? Just like anything else dissipates in energy. And so as I'm far away from somebody who's yelling, it's not as loud to me or intense in physics terms as if I was right there. And so if I'm at some distance away from somebody, I need to calculate the intensity from where I'm at is going to be equal to the initial intensity of the source, or the initial power of the source, divided by the radius, how far away I am from them. And then this is just radius of a sphere because sound travels out in 3 dimensions and in all directions, right? So I need to figure out the intensity. If I'm far away, or if I'm right there, then it's just power divided by area, right? And so we take this intensity in watts per meter squared, and we get it into decibels. This is represented by the symbol beta and in equations, and then we abbreviate decibels as D capital B. And so what I take is I take this intensity that I got from up here, I divide by I naught, which is just a constant, it's that number, and I multiply it out by log 10. Once I do that, I've converted intensity in watts per meter squared to sound intensity in decibels, right? And that's something that makes a lot more sense. The decibel scale is a logarithmic scale, which means a couple of things. In order for something to be perceived as twice as loud, right? And so if I go from 1 decibel to 2 decibels, or 2 decibels to 4 decibels, then it has to have at least 10 times the intensity, right? And so it's not just twice the intensity equals twice as loud. Because this is a log 10 scale, actually it would have to be 10 times as intense to be, quote, twice as loud, to register twice as loud on the decibel scale. So if a stereo's intensity is increased by 100 times, how much louder is the sound perceived? Well, the sound is 3 times as loud. Even if the intensity is increased by 100 times, the sound's intensity or perceived intensity in decibels is going to be 3 times what it was originally. Okay. All right, we're going to move on to the last idea about sound, which is that of the Doppler effect. And the funny thing about the Doppler effect is you've heard it, and you hear it a lot. The Doppler effect happens when any source, right, emitting a sound, just like this is emitting a sound, begins to move. The sound that source makes is constant. It's got its own frequency, it's got its own wavelength, it's got its own amplitude. But as soon as that sound source begins to move, if people are kind of standing by and this begins to move, what we hear is a shift in frequency. We hear the pitch change, right? And so you think about a car driving by you, or somebody yelling out the window, or a car horn honking as it continues to drive by, maybe like a train horn honking as it goes by. And then what you hear is a really, really low frequency that increases as it gets towards you and then fades out again as you leave, right? And what happens is as this source is emitting a sound and traveling in a direction, it's actually catching up with its own sound waves. And so while the frequency, if you're in this little car, is the same, if you're an observer on the outside and you're just standing still, you experience a shift in frequency because this guy is catching up with his own sound waves and thus kind of effectively changing the wavelength of the sound that you hear as an observer. And so we hear this area of very, very high frequency, so high frequency in front of the car, and then low frequency waves or kind of long wavelengths behind the car, right? Mach 2 is a really interesting thing too. So things can actually go faster than their own sound waves. And when they do this, we say that they've broken the speed of sound. And so the physical velocity of the object is faster than the sound that object is emitting. And this is breaking the sound barrier. So Mach 2 is kind of common terms for traveling twice the speed of sound. Right? And we have fighter planes that can do this. The space shuttles do this when they land. Growing up in Florida, I heard it all the time. And when something breaks the sound barrier, it creates what we call a sonic boom or a shock wave. And so as these shock waves are kind of catching up or trying to catch up to the object, they are in such a completely energized state that they actually condense the air around them, create clouds, and create this massive shock wave called a sonic boom, right, that we hear as a really, really intense sound as a result of that. All right, so we have our two kind of Doppler effect formula sections talking about the frequency of a sound perceived. There we go. And so sometimes the source of the sound is moving, like a car, right? Or sometimes we as the observer are moving, like us moving past a big festival or a parade, right? And so the first thing that you want to determine about a Doppler situation is the source moving and the observer is standing still? Or is it the other way around? Is the source standing still, like the carnival, and the observer is moving, like driving by? And so determine what you're doing. And then within each of these sources, we've got formulas for approaching and leaving. And remember, as you approach, you hear a high frequency sound. And as you leave something, you hear a low frequency sound. So approach should be high frequencies and leaving should be low. And when I say high and low, like higher than the sound being emitted and lower than the sound being emitted, than the true frequency of whatever that sound is. And then just a little reminder about changing between intensity and decibels, right, for non-moving sounds. And so have fun, right? These are going to be your homework problems, page 503, numbers 17 and 18. And then 21 to 23, 26, 27, 28, 34, 36, 37, 39, 41, and 44. Or 41 through 44. You'll realize in this chapter when you go to look at the homework that we're really jumping around, right? We're kind of jumping right into 17. And the reason is chapter 15 also covers electromagnetic waves, which is all of next semester. And so congratulations. This is your last lecture in Physics 111 for fall 2014 semester. Go ahead and try your homework. Let me know if you have questions, and I will see you guys in class.